My name is Jayson Patrick. I'm the Technical Director at Electrotechnic. And this presentation is a technical presentation about accurate high voltage power cable current calculations. Here's a high level webinar agenda. I will speak to you about IEC 60287, which is the penultimate standard for cable current rating calculations. I will speak about CIGRE Technical Brochure 880, CIGRE Technical Brochure 908. I will show you the equivalent thermal circuit according to IEC 60287. I will speak about cable modeling with a brief demonstration of a HVDC cable model. I will talk to you about electrical losses, thermal resistances, and multiple circuit calculations with a demonstration. I will not be speaking about the finite element method today. I will briefly introduce you to the software that has been used for the modeling, ELEK cable HV software. That's accurate and validated software for cable current rating calculations in accordance with IEC 60287. It can do any AC voltage cables or HVDC as well. It complies with IEC 60287 and has been fully validated with CIGRE Technical Brochure 880. You can model custom cables and you can determine cable current ratings for your specific installation conditions. IEC 60287. Hopefully a lot of you have heard of that series of standards. There are actually 9 parts to that standard. It's a very comprehensive set of documents all around cable current rating calculations. Actually, it's applicable for low voltage cables up to any AC voltage, and also DC up to 5 kilovolts. With an extension required for HVDC, which I'll speak about a bit later. We continue to use this standard. It's widely adopted. It's still widely recognized. It's suitable for common cable types and a lot of typical installation methods that we still use. It's renowned or understood to be reasonably accurate. It's therefore reliable and suitable for current rating calculations for new and existing cable circuits. By using IEC 60287, we can ensure consistency and comparability of our current rating calculations between different suppliers, designers, bidders, etc. I should mention, and if you've ever looked at this series of standards, that it is quite complicated, very complicated in parts, although it's mostly analytical equations. But there are a lot of equations, and putting them all together is difficult, and there are many gaps in the standard. This is the equivalent thermal circuit as prescribed by IEC 60287. We have a series of, so the cable is represented by a series of electrical heat sources or losses. Those are the W terms. So heat is generated within the cable. For example, of course, in the conductor, but also dielectric losses in the insulation and other metallic parts, if they are present, dissipate heat within the cable, cause it to heat up, and applies limitations to the current capacity. And of course, surrounding those heat sources, we have thermally insulating layers, such as the insulation, etc. And those pose thermal resistances in line with the heat generation sources within the cable. So within the cable, we're talking about all of the W terms there. And then also from T1, thermal resistance T1 up to T3 is all within the cable. Then the thermal resistance outside of the cable, T4, is also very important. Now, there are two approaches to that. You could use the analytical equations from IEC 60287, or you could use an FEM approach. But that is as far as I will go with FEM today. And there is the general current rating equation down the bottom, which is down the bottom of the slide, which is solved typically iteratively. So it takes a number of iterations to solve for current capacity, because a lot of these values are temperature dependent, for example. Let's talk about the new, or quite new, CIGRE technical brochure 880. The title of that technical brochure is Power Cable Rating Examples for Calculation Tool Verification. Now, my understanding is that a lot of work has gone into this technical brochure, and if you refer to it, it's very extensive. It was there are a number of years it took to develop. There are 11 benchmark examples, so fully worked examples of IEC 60287 calculations. There are 49 guidance points. These are generally in addition. They're attempting to fill the gap or fill the gaps in IEC 60287. Now, the reason this technical brochure was developed is due to the ambiguities in IEC 60287. What was happening was there were many different vendors or people performing these calculations and essentially coming up with different answers. Therefore, this technical brochure was kindly developed by CIGRE, and it provides enough case studies, well, not quite enough, but quite a number of case studies for us to verify a lot of standard installation conditions and a number of different cable types, so that we can all arrive at the same answer and we're doing the calculations properly. So CIGRE TB 880 currently reflects the views of working group experts. These are world-renowned experts in cable rating calculations, and it is regarded as the current best practice in current cable current calculations, cable current rating calculations. I should point out that our software, ELEK Cable HV, has been fully validated against that technical brochure. Our software can model all of the case studies, all of the cable types, and we have complete matching results up to 11 decimal places. So I can be very confident in the results that I'm presenting to you today. I'll also mention CIGRE technical brochure 908. This is a little bit more recent, very recent actually. This is about a specific use case, which is Armour losses in 3-core cables. Now, this was also developed by a working group of experts, and it was brought about because particularly around 3-core armored submarine cables, the industry was convinced that the losses in the armor, metallic armor, particularly steel wire armor, was too conservative, and it was derating the cables, particularly submarine cables, too much. So they did a lot of studies using empirical equations, but also using the finite element method. It's a very detailed technical brochure, and they have developed a couple of methods for dealing better with 3-core armored cables with steel wire armor. And in general, the result is that the current ratings for these types of cables are actually increased by around 10%, which these experts and the industry regard as more appropriate. Our software, I should quickly mention that our software, we have fully implemented these guidelines as well for these types of cables. And I will also demonstrate that very quickly in the slides. Let's talk about a very important step in HV cable rating calculations, of course. That's modeling in detail. If we want or need accurate cable rating calculations, we need to model the cable in detail. That means modeling all of the metallic layers, from the conductor to the sheath, the armor, etc., whatever's there, and all of the insulating layers as well in detail. Their material types, their diameters, thicknesses, their thermal resistances, etc., dimensions. Those we need to, we usually do that by obtaining a manufacturer data sheet, which should hopefully contain all of that information. Most often it doesn't. There are gaps and inferences we need to make about the layer materials and the thicknesses and diameters. There are mistakes often in these data sheets, but it's a very good start for us to have one. A lot of manufacturers are a little bit secretive about these data sheets because of their intellectual property. So obtaining them can sometimes be a little bit difficult. In our software, we include a few hundred pre-modeled cables in a database, so that could help you to get started quickly if you're doing a tender, for example. Let's talk about what CIGRE TB 880 says about modeling cables. It tells us that we should prioritize the diameter of the layers over the thicknesses in the cable data sheets, and that we should avoid combining layers of different materials in a cable model, which is an approximation. We should model all of the layers that we can in separate layers with separate properties. In good software, you can do that. You can add custom layers. You can see on the left side of the slide, there is the cable manufacturer data sheet, an example that is a 3-core submarine cable, which are very popular these days. And there's the equivalent software model on the right. And they should be like for like. They should match. Let's talk about some important points about cable modeling. Diameter of the layers. So often layer thicknesses do not correspond with layer diameters in the data sheet. This is an example of a single core 132 kV cable, copper conductor, and it's got the thicknesses, nominal thicknesses. If you can see in the top right hand side of the screen, nominal thicknesses and then approximate diameters. Now, CIGRE TB tells us to prioritize the diameters if there's any discrepancy. There is a discrepancy in this data sheet, and this is actually a data sheet from the technical brochure. So if we add up, starting from the diameter of the conductor screen, now if we're adding the insulation layer, we can see that the insulation layer is specified as 16.1 millimeters. Now, 2 times that plus 46.7 will give us 78.9, which doesn't match with 80.5, which is the diameter. However, as I mentioned, we should use the diameter, even if it doesn't match with the thickness that's been specified. And we may need to increase the thicknesses of layers to accommodate. And you can see on the left-hand side the custom software model for this cable, and the yellow areas for custom layers that we've needed to add to model this cable. Let's talk about XLPE insulation. XLPE insulation is very popular these days, of course. It has very good performance. That's the reason. Now, in the standards, in the calculation, whether the XLPE insulation is filled or unfilled, that's a material property. Very often that's not specified, and we can see that in the data sheet here, that it simply says XLPE. CIGRE Technical Brochure 880 specifies that if it's unknown, we should assume that it's unfilled. Now, if we look at the constants, epsilon and tan delta, relative permittivity and the loss factor that are given by the IEC standard, we can see there are different values for different types, unfilled or filled, and different voltage levels for XLPE insulation. So actually the filled insulation has greater dielectric losses, so it's actually more conservative. But CIGRE TB 880 tells us to assume unfilled if it's not specified. Let's talk about helical tapes that are wound around wire screens. The purpose of these tapes is to electrically interconnect the screen wires. Now, according to the technical brochure, we should not include these tapes, metallic tapes, in our cable model. Very often, the number of you can see for the wire screen, 140 millimeters squared has been specified. Now we need to model that in software. So it's made up of wires. So we are usually given a wire diameter, but we may not be given the number of wires. And we need to adjust, it's a simple thing to do, but we need to adjust the number of wires to match the area of the screen to produce a good model of the cable. In this case, the data sheet didn't include the number of wires, though we could work out the wire diameter. So we needed to specify that there were 57 of these wires, and that approximately matched 140 millimeters squared. Moving on, let's talk about complex paper insulated cables. In this example, and it's quite common for high voltage paper insulated cables, that the insulation may consist of multiple layers with different thermal properties, paper layers of different paper types, and therefore they have a different thermal resistivity, and they need to be modeled separately as separate layers, but they also need to be combined as a single main insulation, such that we can properly calculate the dielectric losses, the voltage-dependent losses within the insulation. Again, in this data sheet, there was also some discrepancy between the thicknesses specified, the nominal thicknesses. If you add those up and you work out the difference in the diameters, there's a discrepancy there of 0.5 millimeter, and we needed to include that with the main insulation. We need to consider the diameter over and above the thicknesses that have been specified. Now, you'll notice the thermal resistivity of those paper layers. We've got an inner and an outer kraft paper layer, and the thermal resistivity of that type of paper is different to the middle type polypropylene laminated paper. As I mentioned, 3 layers of insulation are combined for the dielectric loss calculations. This is very important. Otherwise, we would underestimate the dielectric losses within the cable. Dielectric losses are also a heat source in the cable. Let's talk about the intricacies of modeling cables with double armor, so 2 layers of adjacent layers of armor, and also similarly pipe type cables. So when we're modeling these cables, we need to include the metal pipe and any coating over the pipe. You'll see that in the model, and skid wires importantly. We need to model the cable exactly. Same goes for the for double armored cables. This is quite uncommon, a double armored AC cable, but it would be more common for a double armored DC cable. But if we're talking about the loss calculations, only the first layer of armor needs to be considered for the loss calculations. And CIGRE Technical Brochure 880 regards or advises us that the magnetic fields are shielded by that first layer of armor. Therefore, the losses in the second layer of armor can be neglected in the loss calculations. That's the same goes for the metallic pipe in a pipe type cable on the left. The metallic skid wires shield magnetic fields, and therefore the electrical losses within the pipe can be neglected in the calculations. But nonetheless, especially in the case of, well, in both cases, there are insulating layers between both armors and on the pipe, and that all still needs to be modeled because it's a thermal resistance. Let's talk about modeling of HVDC cables. This is a bit of a special case because there are 2 limiting factors with HVDC cables. There's the normal thermally limited rating typical of IEC 60287. You saw the equation. But there's another limitation, and that's an electrical stress limitation. This is all to do with the space charge effect within the insulation caused by the DC fields. And you can see a couple of plots here about the phenomenon on the left. Under normal operation, starting from this is electrical stress within the insulation. Under normal operation, from the inside or the inner part of the insulation towards the outer, you'll see a reduction in electrical stress. Now, what can happen at actually different operating temperatures? This is temperature dependent. You can see an inversion in this effect. So what happens is you actually end up with higher electrical stress on the outer edges of the insulation or the dielectric, and this gives rise to this electrical stress limitation. So it's voltage dependent and also temperature dependent. There is the cable manufacturer definitely needs to advise you about this electrical stress limitation, and that is actually translated into a temperature across the dielectric limitation, which I'll demonstrate to you in the software quickly. If you don't have any information, you can assume something that's added in the footnote here. Let's look at in a little bit more detail about this is an example of a HVDC cable model. It's a double armored submarine export cable, 320 kV DC, single core, 2000 square millimeters. Now, as I mentioned, you can see the software cable model on the top left, all of the different layers, including custom layers. There's water blocking tapes, that several tapes that need to be modeled as custom layers. And both of the armors need to be modeled as well, even though the electrical losses will be negligible in them because it's DC. Now, highlighted in the middle of the screen, you'll see an input for maximum permissible temperature drop across the insulation. That is unique to modeling HVDC cables. Just as an example, we are showing an FEM mesh plot for this HVDC cable. Now, highlighted in yellow very quickly, again, this cable, HVDC cable, has two limits. One for continuous operating temperature, 70 degrees, and it has a maximum temperature drop across the insulation. That's also a constraint related to this electrical stress limit. So when we rate the HVDC cable, we need to rate it according to both limits. Let's look specifically at electrical losses. We're going to talk about resistances, conductor resistance, other metallic layers that of course have resistance. We're going to talk about lay length, dielectric losses in the insulation caused by voltage stress, metallic screen and sheath losses, metallic armor losses, and metallic pipe losses. So in the equivalent thermal model by the IEC, you can see highlighted in red where the electrical losses are generated, starting with the conductor. Let's talk about conductor resistance. Conductor resistance is temperature dependent, as we know. DC resistance is normally given to us by another IEC series of standards, IEC 60228. It's typically given to us at 20 degrees, so we need to scale it with temperature, and we also need to adjust it to be an AC resistance by considering skin and proximity effects. The CIGRE technical brochure prefers that we use DC resistance from those IEC standards. There is one for metric conductor types and one for imperial conductor types. Lay length correction is also very important to consider. As I mentioned, the technical brochure prefers that we do not use DC resistance values from manufacturer data sheets or measured values, or that we shouldn't use calculations, because you can obviously calculate DC resistance. I guess this is all about consistency. And when we adjust DC resistance to be an AC resistance, which has greater losses, which we need to do, AC resistance depends on skin effect and proximity effect. There are separate calculations for that. They are more or less quite detailed. And there is an additional point 2 here about AC resistance, mentions that there is an additional multiplying factor of 1.5 for cables with magnetic steel armor or pipe type cables. That is according to the IEC 60287 standard. CIGRE technical brochure 908 says something a bit different about that. It doesn't exactly agree with it. It's probably simplistic in regards to that brochure. And we must correct for lay length of the conductor strands when we're calculating an accurate AC resistance. The resistance of other metallic layers. Other metallic layers can include screens, sheaths, and armors. They need to be calculated. It's usually not. We usually don't consider the AC resistance, except for armor. This is because the skin and proximity effects are regarded as quite negligible for screens and sheaths. We calculate DC resistance for those metallic layers based on their material, a number of wires, construction, being there. If it's a solid sheath or a corrugated sheath, we essentially consider the area of the metallic layer, and we calculate an accurate DC resistance. There are some factors for converting smooth sheaths into corrugated sheaths in terms of DC resistance. Armor is a little bit different. Of course, there can be even higher losses caused by armors. So we must, if you're dealing with wires, we must always consider lay length and apply a lay length factor to increase resistance. IEC 60287 specifies that we must increase DC resistance of armor wires by these 20% or 40% for these different wire diameters respectively. And CIGRE technical brochure 880 tells us that if we are outside of those diameters, that we should apply linear interpolation to get a factor for increasing the DC resistance of armor layers. It's an equivalent AC resistance for armor. Let's talk about lay length factor. This is very important to consider. It increases resistances by considering the stranded, how the strands are wound, and how that increases their effective length, and therefore increases their resistance. And we need to correct for that. It also, when we're talking about multi-core cables, 3-core cables, for example, we also need to correct for core lay length, and that even affects capacitance, which affects dielectric loss calculations. And actually, if you get down into the equations, lay length correction affects the degree of cover calculations and thermal resistance calculations, actually. Dielectric loss is the electrical loss within the insulation. Losses occur in the main insulation except for DC cables. It depends on the insulation thickness, obviously the material, loss factor. Those factors are given by the IEC standards. Losses are voltage dependent. You can see the equation there for dielectric loss, which increases with the square of the voltage. Now, importantly, IEC 60287 in the past, you'll see the table on the right here, used to tell us, well, it still tells us that dielectric losses can be neglected at voltages for these insulation types at voltages less than this in the table. So we can say that dielectric losses would be 0. However, CIGRE Technical Brochure 880 disagrees with this and tells us that we must always consider dielectric losses, and it's based on capacitance calculation and these loss factor tan delta values taken from IEC 60287. Let's look at a quick example about dielectric loss. In this example, it's a 400 kV cable, so dielectric loss would always be quite reasonably significant. It's never as significant as the other losses. You can see total losses, conductor losses are a bit hidden there, and sheath losses depending on the bonding arrangement. It's always a bit less than those losses, but it does add additional heat to the cable. And as you can see in this example, if we didn't consider it, there would be we would actually overestimate the current rating by around 80 amps, which is around 8% in this case. So we must always consider dielectric loss. Let's talk about the losses or loss factor as it's referred to in IEC 60287 in the sheath, metallic sheath and screen layers. IEC 60287 defines sheath and screen loss factor as the ratio of the total losses in the metallic sheaths and screens respectively to the total conductor losses. It's like a ratio. So screen and sheath loss factor consists of two parts, circulating losses and lambda 1 and eddy current losses. Sheath and screen losses are dependent on bonding arrangement, of course. Sheath circulating currents can be very significant, especially for solidly bonded cables. A multiplication factor of 1.5 is applied to the circulating current loss factor for cables with separate sheaths. That's according to CIGRE Technical Brochure 908, which we'll talk about. Sheath eddy current losses should always be included. They're always there, and they will always be included irrespective of the bonding arrangement. They'll always be lower than circulating current losses when we're talking about solidly bonded cables. But they need to be considered, and actually circulating currents in the screen will actually reduce eddy current losses even further. Let's look at a very quick example which just shows this is a 400 kV cable, which with solid bonding, which is not. I'll grant that's not a normal case, but you can see that even with respect to the conductor current rating, 850 amps, the Sheath circulating current is almost as much, over 500 amps is flowing in the sheath. And you can see the losses down the bottom. You can see conductor loss, dielectric loss, voltage dependent losses, and the sheath loss, which we're talking about. Let's look at this this factor that's present in the new CIGRE Technical Brochure TB 908. The additional screen circulating current loss factor. By considering it, we are effectively reducing the current rating ever so slightly. Let's talk about armor loss, the armor loss factor according to IEC 60287. Three core cables with non-magnetic wire armor, the armor losses are 0. For cables in metallic pipes without armor, the pipe will act as the armor. The cables in metallic pipes with armor or cables with double armor, only the inner layer needs to be considered. We already mentioned that. Let's look at the additional considerations of CIGRE Technical Brochure 908. Now, just remember that this technical brochure is only applicable for cables with a single layer of round wire metal armor. This 1.5 multiplying factor in the IEC standard, it suggests, is conservative. It considers the effect of magnetic armor, so the effect of the armor essentially on the sheath losses. It considers lay direction of armor. So these are additional factors in addition to the IEC standard, and it also throws in another factor, which is the complex magnetic relative permeability of the armor. That's another factor that's considered when you want to apply the calculations in that technical brochure. And the implications of implementing armor loss calculations in accordance with this CIGRE technical brochure are that conductor and sheath screen losses will considerably increase, which seems counterintuitive, but they're not. We're looking at the overall effect. Armor losses will be significantly reduced with the method in this technical brochure, and the overall effect, and what you'll see generally, is if you work out armor losses or current rating according to this technical brochure 908, you'll see roughly an increase in current rating or current capacity of these types of cables by around 10%, which is significant. Let's look at a real example. As I mentioned, so if you do the calculations on the left, this is one of the case studies in technical brochure 880. If you do the calculations in accordance with IEC, and then technical brochure 908, you do a better, improved armor loss calculation, you can increase the current capacity of the cable by 10%, which is really quite significant. Let's talk about the thermal resistance components of the calculation. Of course, they're part of the calculation, but they're a representation of the cable. T1, T2, T3, those are thermal resistances inside the cable. The definitions are there. and there are separate calculations. We need to combine the thermally insulating layers and custom layers if they're present within the cable. We need to lump those into these calculations, and they will be used finally to calculate the current rating. There are various correction factors applied depending on the cable construction as well. Let's talk about the external thermal resistance to the cable. External thermal resistance is possibly the most interesting thermal resistance, that's for sure. This is, it depends on the external thermal environment, which is highly variable, can depend on those objects that are in very close proximity to the cable, including the duct, any filling material inside the duct, be that air, water, or a solid material. Also, if the cables are buried, that could be the soil or the backfill. So the external thermal resistance calculation, and that can be quite involved, considers the cable circuit configuration. So it starts at the external environment to each individual cable, whether the cables are within the same circuit, whether they are touching or spaced. The equations are modified for T4 depending on that. And then the mutual heating between the circuits is also included in the T4 calculation. And the T4 calculation is highly dependent on the installation and the environmental conditions. For example, different installation conditions, and I don't think this slide has been set up correctly, but cables in air could, there are different examples of installation conditions. Cables in air, groups of cables in air. These installation conditions have a different external thermal resistance calculation, T4 calculation. There's a different method of calculating them because they're very different. Buried cables, direct buried cables with or without soil dryout, buried in backfill, airfield troughs, tunnels, risers and J-tubes in water, for example, or multiple backfills in FEM, that's a different T4 calculation. Let's look at multiple circuits. For multiple circuits, we're talking about buried here because it's the simplest. The mutual heating must be considered, but the same goes for cables in air as well. For touching cables, the temperature distribution in the individual power cables is distorted, and the IEC equations are actually adjusted for this distortion. So those are empirical equations. Otherwise, you can use FEM. So there's an image here of a mesh. A meshing of a circuit of touching cables. That is ideally the best way of calculating the temperatures, the most accurate, but you can use the adjusted IEC equations for touching cables. For the non-touching cables or for the mutual heating between multiple circuits, the calculation of mutual heating is based on the Kennelly hypothesis, essentially the method of images and the superposition theorem. And you can see in the top right-hand corner, you can see it's a buried installation. There's a backfill, and you can see the temperature contours. So all of the individual cables are mutually heating each other, and so are the circuits. And we have an overall temperature profile, which is displayed in this temperature contour plot. and that's all affected by the mutual heating. Interestingly, we have marked the hottest point on the backfill area actually, and obviously that makes sense that it's at the center of the backfill, and it's also at the deepest point on the backfill as well. That's where it's going to be the hottest. Now that we've gone through a lot of the calculations, let's have a brief look at some calculations. Just bear with me while I change the screen. I might just quickly show you some of the cable models that we spoke about. This is the HVDC cable model. I'll quickly, it's already pre-modeled. I'll quickly go through some of the layers. So obviously there are general settings. We need to set the cable type, the number of cores, whether it's DC and the voltage level. There are the conductor layer is a very important layer. We need to set the conductor size. Where do we get the DC resistance from, conductor class, materials, etc., and the conductor type. And the DC resistance comes from the standard as recommended. There are some additional properties that can be set. Some of them are particular for transient calculations or even crossings, cable crossing calculations. There are some custom insulating layers for water blocking tapes, conductor screen, the main installation itself. We can have custom layers, and if we use these standard layers, then we'll pick up these standard thermal resistivities, etc. There's something about the cable capacitance, which is related to the insulation. There is non-corrugated sheath, a bedding for the armor, and then the armor layers itself. This is double armored cable, and then on the outside we have polypropylene yarn, which is very typical of the submarine type cables. I might just quickly show a 3-core cable. This is how a 3-core cable looks, and the different layers. But essentially, we can customize the model, and that's what we need to do based on the data sheet. We need to add different layers or custom layers as required to match the dimensions and the materials of from the data sheet. With that, then we can set up the model depending on the installation conditions, and we can model different cable types. In this case, I'm using a backfilled installation with a single backfill. This is all fully interactive. You can drag and drop cables. You can have different cable types within the same installation. The calculations are performed live. So I mentioned in the presentation about different loading settings. There's isolated ratings. Actually, in isolated ratings, the mutual heating is completely ignored. It's not the most widely used setting. the most common setting would probably be unequally loaded. So in this backfill or backfill arrangement, I've got six separate circuits. These are all mutually heating each other, causing derating. You can see that the current rating for each of the circuits in the unequally loaded setting is displayed. All of these cables are operating at their maximum insulation operating temperature, which is 90 degrees. And the circuit in the middle, it has the lowest rating because it's mutually heated the most, which makes complete sense. If we look at the soil temperature plot, you can see how the mutual heating is working. And I will also just show you the equally loaded setting, which is a very interesting setting. It actually takes quite a few more iterations, actually a lot more iterations. But what we do is we can balance the current between all of the circuits. So it will be the current rating of the lowest rated circuit, which was this circuit 1, which will dictate the rating of all the others, and then we balance out. Well, that circuit 1 will run the hottest at the 90-degree limit, and then all the other circuits will have that current applied to them, and obviously they won't be running at maximum temperature. So that concludes the presentation and the brief demonstration. I'm now open to questions. So I will take them now.
Good question.
Yeah, we can hear.
My question.
Yeah, go ahead.
Okay, so the first question is why do we specify unfilled XLP if it is not specified in the cable data sheet?
Why do we specify unfilled? Well, if it's not specified. Well, importantly, CIGRE Technical Brochure 880 tells us, but the reasons predominantly because unfilled is much more common than filled, and filled, which is a process of adding additives to the insulation, is a deliberate process. It's a costly process, and I dare say that it's more applicable to EHV cable installations, and I would suggest that if your installation is filled, that you'll most likely know about it, or you'll be informed about it. Unfilled is much more common.
So the next question is, can you model pipe type cables filled with thermal sand?
Edson, I don't think that we can model pipe type cables filled with thermal sand.
Yeah, we can do that in a duct.
Oh, we can do that in a duct. Yeah. Yep, we can probably do that. Reach out to us if you would like a demonstration or more information.
Question is, can we do 415 volt cables in cable HV, or should we go to cable to web, some other software?
Should we use cable HV for low voltage cables? Yeah. Look, you definitely can. It really, in my view, it depends on the importance of the circuit. So if you're talking about large cables, high loads, important circuits that can be high cost, it's better to have an accurate rating of the cables, which cable HV will definitely give you, and it will most definitely end up saving you money on the cables and the installation if you model it with better accuracy. In fact, in the low voltage cable rating standards, actually those, you should be aware that those current rating tables are conservative, but they are calculated using the same methods as cable HV, but they're set up for generic conservative conditions and conservative cables. You'll get a better result and a more accurate result that can save you money if you use cable HV.
Okay, the next question is probably I will take it. So I think in TB908 we have Armour magnetic permeability calculations. So will those calculations or those values affect IEC 60287 calculations? So that's a question. So to answer the question, if you use IEC methods, you have two permeabilities that you have to specify. One is the longitudinal and one is the transverse relative permeability. And those are not complex numbers. But what TB908 says that, or if you read through the measurements, you would see that these are complex parameters. So if it's a complex number, you would have to convert it into an equivalent number and then use it in IEC 60287. But if you get your real-time measurements, you would better be using CIGRE TB 908, which will give you much better results than higher current ratings than IEC 60287. Another question is, Jayson, does our software do multiple cable crossing cases?
Yeah, does our software do multiple cable crossings? It absolutely does. So we have extended the IEC method to deal with any number of circuits that are crossing. I've seen 17 circuits in a solar farm case from a customer. That's no issue. Yeah.
And the last question that we have is, what are the software limitation for cables installed in air in terms of parallel circuits?
Yeah, cables, limitations of cables installed in air. So cables installed in air is actually much more complex than be they buried, because we're dealing with convection of the air, and that's not well, I guess it's, in terms of cables, it's not been well modeled or measured, or it has been, but only for specific arrangements. And therefore, we are limited to specific arrangements of the cables for cables in air. Also, there is an IEC, part of IEC 60287, which covers groups of cables in air. We also have covered that. And that talks about, allows us to model the mutual heating of cables, multiple circuits in air, and to model that effect, but that's also limited to certain configurations. However, there are ways around it by combining different calculations. We can explain that to you if you'd like to reach out to us.
Yeah, last one. I think one last question, which I think important, is what about load factor and loss factor? If you can.
Do you want to take that one?
Yeah, I can take that one. So let me find no. So the loss factors are load factors. Daily load factors is an input into the software for each of the cables. So any load factor can be input. I mean, any load factor 1 or less than 1 can be input. And these load factors, typically they would change your external thermal resistance is modified depending on the load factor. So you could have, so the external thermal resistance, when you talk about it, it can be for the backfill, it can be for the soil. All these thermal resistance would be modified if you use an external a load factor. Just if you can just show them where we input the external load factor for any one of the cable model that you have on your.
Oh, I see.
Yeah, any one that you have on your. Yeah, so if you see here, we have an input for daily load factor. So you can add it for any of the cable models that you have in your database, and then that would change your T4 correction factors, and then that would change your cable ratings. Yeah. I'm afraid we have time only for this much, but we would be happy to respond to you, to your questions. If we have missed anything, please feel free to email us any questions you have, or if you'd like to have a free demo of the software, please let us know, and we'll be excited to share information with you. Yeah.
Yeah, thank you everyone for attending the webinar. As Edson said, if you would like to reach out to us, we'd love to chat with you. You can visit our website. There is a free trial of ELEK cable HV software. It's fully functioning. Thank you again, and I hope everyone's learned at least something. Thank you, and we'll see you again. Thanks, Edson.
Thanks, Jayson. Thank you.